Hello everyone, welcome to Stat 479, Lecture 18. So we're still in we're at kind of the final stages of defining our overall statistical model, which is a graphical model. And in particular, we're going to talk today or finish our discussion on undirected graphical models, which are graphical models which correspond to undirected graphs. And then we're going to talk about connections to linear models in GLMs. So what we learned in the first 2 or 3 modules is going to come in very useful for this part. And we're going to see kind of a nice connection between undirected graphical models and linear models or GLMs. And then I'm going to finish with an overview of DAG models and undirected graphical models, and then we're going to kind of move on to like the next bit, which is kind of where you want to actually do some estimation and statistical inference with these models. So the last 4 lectures or so is really just focused on defining the models, and then we're going to move on to actually doing some estimation inference with these models. So just as a reminder, just like all graphical models, there's 2 components. There's a graph and there's a distribution. So for undirected graphical models, there's 2 components. The first component is an undirected graph, which includes a set of vertices x1 through to xp. x1 through to xp. And then we have a set of edges, or a set of undirected edges. So in particular, a couple of the examples that we've seen. So we have this graph with 3 nodes, x1, x2, x3. And the edge set here, there's 2 edges, one from x1 to x3, and the other one from x2 to x3. And similarly, if we have a graph with 4 edges here, the nodes are x1, x2, x3, x4, and there's 4 edges, x1, x2, x2, x3, x3, x4, x1, x4. And remember, for undirected graphs, it doesn't matter which node comes first when you're defining the edge, because the edges don't have any direction to them. Then in terms of the PDF, or the probability, the distribution of this p-variate distribution, there's, as we remember, there's kind of 2 components. There's this notion of factorization. So how does the distribution factorize? And then there's also this notion of conditional independences or dependences. So for undirected graphs, the factorization is not as easy to define as it is for directed acyclic graphs. So for factorization, you kind of define things not in terms of conditional distributions, but in terms of the factorization, in terms of potential functions. So in particular, it can kind of be written in terms of 1 over z, where z is this normalization constant. And then there's these potential functions, cjk, xj, xk, where these potential functions are non-negative. And then the way that the graph structure enters is this is only you only need potential functions defined on the edges. So in particular for the first graph here, which is x1, x2, x3, there's 2 edges, so there's going to be 2 potential functions, x1, x3, and 1 for x2, x3. And then for the graph with 4 edges, there's 4 potential functions, 1 for each edge. And then there's this notion of conditional independence or dependence, where this notion of neighbors of a node are really important. So remember that neighbors are just the set of nodes that have an edge pointing from that node to the other node. And so there's a conditional independence given the neighbors of a pair of nodes, if and only if there's no edge from xj to xk for g and ve. So for example, for the first graph, we have that x2 is x1's independent of x2 given x3, and then we have x1's dependent on x3 given x2, and x2 is dependent on x3 given x1, and then similarly for the second graph, which I'll just draw here. we did this in the previous lecture, so I'm only going to list the conditional independence that we have here. So we have that x1's independent of x3 given x1, x2, x4. And then we have that x2 is independent of x4 given x1 and x3. Okay, and so just to, the concrete example that we've kind of referred to so far is so if we consider the multivariate normal with the mean of mu and a covariance of sigma, if we define our our inverse matrix, then we know that the distribution kind of has this form. Where there's the determinant of omega to the half, and then okay, and this sort of shows where the potential functions come in, because you have, you can see that if omega jk equals 0 implies that no edge between xj and xk in. Okay, and so this is what we've kind of seen so far, but the next thing we're going to look at is that so we're going to think about this from a couple of perspectives. What if we have a multivariate distribution that we want to represent as a graph G equals VE that is not normally distributed. Or has a different data type. Okay, so this is kind of like when we were doing when we started with the first module focused on linear models, and then the second model kind of was a generalization of that to GLMs, which was dealing with a case where you had data that was non-normal, and you couldn't really model it with a normal distribution because it might have been like binary data or count data or positive data or something like that, and so you kind of needed the GLM framework to be able to deal with that. And then for DAG models, we are able to do this through GLMs for the conditional distributions. We showed how to do this a couple of lectures ago. So remember that, so this is for DAGs. So what I'm talking about right now is for DAGs, not for undirected graphs. For DAGs, we know that we have this factorization. And here FJ that's the conditional PDF or PMF for XJ given its parents. and this should also reinforce that what we're talking about here is DAGs, because parents is a concept that's only relevant for DAGs because the relationships are directional there. And so so we can use exponential family GLM framework to define okay, so this kind of allows you to say, well, so you can just use what we know about exponential families or GLMs, where it's kind of like the response is xj, and then the covariates or features are x parents of xj. So I'll write out the distribution and then just put that down in words. So we have that this is xj okay. So so this is like the it's GLM where response, so we typically refer to the response as y. This is a little bit different and something to get your head around. Here the response is xj, and covariates are x parents of xj. So that's all the parents of xj. And so if we define GLM for each of the p nodes, this defines DAG. Okay, and so this defines DAG through factorization. Okay, and so we saw this, for example, if we have linear SEMs, structural equation models, that's like just a Gaussian exponential family. But you could certainly imagine that if you replace that with a Poisson or a Bernoulli exponential family, you could define your distribution like this. And so that was just a bit of a detour to DAGs, because we want to do something similar for undirected graphs. So for undirected graphs. Okay, and so it turns out that we can, but it's not quite as simple as the case for DAG. So for undirected graphs, so for undirected graphical models, we don't have factorization. In terms of conditional PDFs. But what we do have is that xj is independent of xk given given all the neighborhoods. So this is something that for each j equals 1 to p. And so, So this is something that's pretty straightforward to check. This is kind of, I mean, I'm not going to kind of go into too many details about this, but this statement is actually equivalent to what I wrote earlier. Again, so remember that we've kind of defined things as or maybe I'll just write it like this. So this is the neighborhood of xj given, like except for xk. And so this is actually equivalent to okay. So like, I mean, that sort of seems a little bit complicated, but what we're really saying is that if we condition on the so if we condition on the neighbors of xj, then xj and xk are independent unless xk is a neighbor. So that's what we're basically saying here. So we're saying here that x1 is going to be independent of x3 given the two neighbors of x2 and x4, which we already know, and that x2 is independent of x4 given the two neighbors of x2, which are x1, x3. Okay, and so what that, I mean, and the whole point of saying that is that therefore we can imagine fitting a GLM with response xj, so that's like xj is y in our GLM framework, and covariates x, and then the neighbors of xj, or maybe and the covariance, which will just be the neighbors of xj. So this is exactly, so it's like a DAG, but with parents replaced by neighbors. So so we define undirected graphical model by the P conditionals fj of xj given the neighbors of or I'm going to write it this way here so that okay. So so to take a concrete example, if we have that So we're going to go back to this normal examples because it's kind of probably the easiest one to think about. We're going to have mu sigma again, like we've had earlier. And so we know that the overall model looks like that, and then you can show and that xj equals to if we look at the neighbors of xj, I'm going to say akj xk plus mu j plus epsilon j, where epsilon j is normal 0 sigma j squared. And then you define this for j equals 1, 2 up to p. So another way to think about that is that fj of xj given x neighbors of xj is equal to the standard normal distribution. So okay. To show equivalence between the p conditionals and the joint multivariate normal model is challenging. And it's beyond the scope of what we're covering in this course. The main thing to take away from it is that you can actually show that in some sense you can define the overall model for the multivariate normal by just by linear regression models looking at the neighbors. And so what I can tell you is that you can show that akj is equal to negative omega kj over omega jj, where remember that omega equals to this sigma inverse. So therefore you can see that therefore akj equals 0 if and only if omega kj equals 0. And this is where that that structure comes in, because if omega kj equals 0, that implies that xj and xk are not neighbors. Okay, and so we can define Gaussian or multivariate normal graphical model in terms of p conditional models. And again, the exact correspondence between that is a little bit difficult to show and beyond the scope of the course. I can certainly point you to some references if you're interested in finding out how that equivalence works, but it's beyond the scope of the course. The main thing to note is that we can represent the overall distribution in terms of the conditionals. And then we can extend this to GLMs. So we can define the undirected graphical model as follows. So we define the undirected graphical model as follows. So for j equals 1, 2 up to p, we have the sets neighborhoods of xj, j equals 1 to p. So we have, like neighborhood of x1, neighborhood of x2, neighborhood of xp. And then we say that we can consider a GLM for each j with response xj. So once again, we're doing something a little bit different here, where we're treating the response y as like an xj, and what we're treating as our covariates are just the neighbors of xj. So i.e. what we can say is that fj of xj given x neighbors of xj, that equals to a lot like what we see for the DAG, but with the parents replaced by neighbors. We can use the GLM exponential family form. Okay, and so this graph is defined by parameters AKJ. Where we have to have that xk, xj, and xk is in the set E. Otherwise, you can either interpret that as otherwise akj equals 0, or akj isn't really part of our model. So for example, if xj is binary, we can fit a Bernoulli model. If xj is count data, fit a Poisson model. Okay, so this gives you a way to define the graphical model in terms of its conditionals, or the undirected graphical model in terms of the conditionals. So just to give you, let's be a little bit concrete here. So we have that this is our, and then we have that the neighborhood set of x1 is equal to x2, x4. The neighborhood set of x2 is equal to x1, x3. The neighborhood set of x3 is equal to x2, x4. And the neighborhood set of x4 is equal to x1, x3. So therefore we have that f1 of x1 given, and then we condition on the neighbors, x2, x4. That's going to be h1 of x1, so it depends on what we choose for the family. Exponential family here, and then we have a12, x1, x2. Or maybe we'll, well, that's fine. a12, x1, x2 plus A14 x1 x4, and then minus A1 of A12 x2 plus A14 x4. And similarly, F2 of x2 given x1 x3 equals to H2 of x2 times exponential of A12 x1 x2. Note that A12 and A21 are the same. That's why I'm referring to them as the same parameter here. Plus A23 x2 x3. And then minus A2 of A12 x1 plus A23 x3. F3 of x3 given x2 x4. That's H3 of x3 times x of A23 x2 x3 plus A34 x3 x4, and then minus A3 of A23 x2 plus A34 x4. And then finally, F4 of x4 given x1 x3 is H4 of x4 times exponential of A14 x1 x4, A34 x3 x4, and then minus A4 of A14 x1 plus A34 x3. And then, we note that Hj of xj and then Aj of is defined by the exponential family that we use. So if it's Gaussian, it'll be, our A's will be like, 1 over 2 sigma squared, and the H would just be that 1 over square root 2 pi term. For the Bernoulli, the H is just 1, and then that A is that log of 1 plus e to the theta, and so on. So we really use what we learned in Module 2 with GLMs here. Okay, so one sort of thing I should point out is that it's very difficult to determine overall joint factorization. Remember that the overall joint factorization for an undirected graph was this, which is this 1 over z okay, because z is very difficult to compute. Usually psi jk of xj xk is equal to exp of ajk xj xk when we use the exponential family. Okay, and so this is something that's a bit beyond the scope of what we're doing, because actually computing that z is actually a very, very difficult question. That's a pretty active area of research in general. But what the main thing to take out of it is that you can define the you can define the graphical model, the undirected graphical model, in terms of these neighborhood conditionals, like where you condition on your neighbors. But what's different from DAGs is that in DAGs, the factorization just naturally works out easily. Like if you just condition on your parents and then you multiply them, that gives you the overall joint. That isn't the case for undirected graphs at all, because you have to normalize things, because you're kind of double counting your neighbors, like x1 is a neighbor of x2 and x2 is a neighbor of x1, and that kind of creates issues when you're trying to put it back together in a joint distribution. Okay, so that's sort of everything that we need to know about undirected graphs and undirected graphical models. For now, we're going to now move on to the question of actually estimating and doing statistical inference on these. So just in summary, we have two different graphical models that I kind of wanted to just compare and contrast. So we have the undirected graphical models and then the DAGs. And then we, there's the graph. Then there's the factorization. So let me just. So the graph here. So this is undirected. G equals VE, and this is directed and acyclic. G equals VE. So the notation looks the same, but the edges are directed, and we also have the acyclic structure. And then we have the factorization, which is just that, let me just give myself a bit more space here. That f of x1, x2 up to xp is equal to, this isn't quite going to work. So we can kind of write out the whole distribution as 1 over z psi jk of xj xk. So this is a bit less intuitive than what we saw for the DAG. So for the DAG, it was kind of a lot more intuitive, that it's just we can write this as the product of the J conditionals, where we condition on the parents. And then we have these conditional independences. Which just assert that xj independent of xk given neighbors of xj union neighbors of xk, not including xj and xk. And this is equivalent to no edge between xj and xk in your graph. And then for DAGs, we have the same thing, but replaced by parents. Parents of xj union parents of xk, but not including the nodes themselves. And this is equivalent to no edge from xj to xk in either direction in your graph. And then the final thing is that we've kind of just talked about now, and then just came up as well here. So let me maybe separate this like this. Then we, so we can also kind of connect them to GLM's parametric models. So we can say that for j equals 1 to p, xj is we can define UG in terms of PGLMs with response xj and covariates and the covariates being the covariance being the neighborhoods of xj, and I wrote out the formula for that. And for DAGs, we can define DAG in terms of PGLMs as well, with response xj and covariates parents of xj. Okay, and so that's going to be very useful when we kind of like use these models and try to do some inference with these. So this is just sort of a useful table to just kind of keep things in mind and to sort of know the differences and similarities between undirected graphical models and directed acyclic graphical models. And if anything's confusing there, then feel free to sort of reach out to me or come to office hours. So we've spent quite a while, like 3 or 4 lectures, defining these models because they're quite challenging to kind of define and to think about. So now we're moving on to estimation or inference with graphical models. And the remainder of this lecture is just going to lay the foundation, and then the next couple of lectures, or the last couple of lectures on this module, we're going to talk about how we actually do inference. And this is like that connection to GLMs is going to be very useful because that's going to allow us to essentially do inference through just the GLMs. Okay, so let's return to the statistical framework, which we haven't touched on too much recently because we've largely been spending time on like the second component, which is just defining the model. So here we have our data, and we have unsupervised data in this case. Remember, we've never really talked about y's in our data set here. I equals 1 to n, so we have p, I guess you could say p covariates or features. There's no response here, and then n samples. And then we have our statistical statistical model, and this is what basically the entire last. So this is the graphical model. And so we had that. I'll divide it up. So for DAGs, if we have G is equal to VE, we had that f of x1, x2 up to xp. We could define it in terms of the conditionals, and then we had that each fj is defined through a GLM. And this allows us to define our parameters. So this was kind of how we defined our GLM. Sorry, this is parents. Let me make that clear. Parents of xj, and then okay, and then and then we say that n independent draws from joint PDF. So I've described the model of just the random variable or one sample, but here we're getting n draws like we would for the linear model. And then for the undirected graphs, we have again that g equals VE, but these edges are now undirected. So here we have undirected edges. And then we have, the factorization, as I spoke about, it's a little bit different, and not something we need to worry about too much, but I'll just write it here. It's defined in terms of these potential functions. And so just to take an example, like if we just let psi jk xj xk equal to like exp of ajk xj xk, or I'll just say it's proportional to that, because we might have some other terms involving like xj squared and xk squared, and so then we have the conditionals xj given the neighbors of xj given the neighbors of xj through, again, we can define them through the GLM. So we have okay. And once again we have n samples or n independent samples from so we have n independent samples. And then so our parameters of interest here are AKJ. And these are related to the graph structure. Okay, so this is we've really spent the majority of our time in the last 3 to 4 lectures on this second component of the module. the second component of the overall statistical framework. So now we'll move on to the third component. So this is where we're talking about kind of estimators or statistics. And one thing to note is that there's we're going to use the GLM framework, and we're going to go through that in mostly in the next lecture. Use GLM framework to estimate AKJ for both DAGs and undirected graphs. But then there's going to be two situations of interest. This is what one is where graph structure where you actually know the graph structure a priori. But the second scenario, which is actually kind of more like common in practice, is that the graph structure G equals VE is unknown. And this is really going to be sort of one thing that's quite new in terms of what we cover in the next two lectures. So we don't actually know what the graph structure is. We want to somehow try to estimate the graph structure. Okay. And so this is going to be the focus of the next couple of lectures, and then the final component of analysis or inference is so there's really two how close are estimated AKJ to true AKJ. That's one thing. But then another one that's often more important for applications is that, if the graph G is unknown, how close is true is estimated graph G hat to true graph. Okay, and so this is quite a new thing potentially for a lot of you, is that, you're used to, like, everything in the course we've seen so far involves estimating kind of parameters. Here, what we're actually saying is that we're trying to actually estimate a graph. And so this is related to model selection. So I'm just going to, in the last sort of 5 minutes or so, just set the scene for what that means. So example. So let's just assume p is equal to 3 here to make our life easier. And so your data here is x1i, x2i, x3i, I equals 1 to n. Okay, and so assume graph G equals VE is unknown undirected graph. Is an unknown undirected graph. So in fact, In fact, there are many possible models, many possible graphs to model x1i, x2i, x3i. For example, one would just be that they're all independent, so we'll just say all independent. You could have another graph where, maybe there's, x1, x2, x3. Sorry about that. Let me go back. Okay, and so this is where they're all independent. This is where we have that x2 is independent of x3 given x1. So this is fully connected. And then I'll just do one more. You could certainly have a scenario where you have like what we saw earlier, which is, x1 is independent of x2 given x3. And then there's many, many more. So so there are many, many, many different there are many different graphs to choose from. And then the question, that we're interested in is, how do we use our data to figure out which graph it is. And I've only done this for the case where there's 3 nodes, but imagine if you go up to 4, 5, and 10, or maybe 100 nodes. You can see there's so many different graphs to choose from. So this becomes an extremely difficult question. So in fact, there's like 2 to the p, or like in this case 8 graphs to choose from. Eight graphs to choose from. And so this is what's termed as a model selection problem. Model selection problem that how do we decide which graph best fits our data? Okay, and so that's the question that we're really going to delve into in a little bit of detail in the next couple of lectures. And just as a bit of a hint, it's going to be very connected to what we learned about with the lasso and L1 regularization. Remember, I sort of also motivated that through model selection, and so that's what we're going to be doing and using for doing our inference here. Okay, so that's everything that we'll talk about today, and then in the next couple of lectures we're going to address this question. Thank you.